This is the introduction to the realization of digital twins for intelligent manufacturing. Based on the R&D achievements of the past projects, the Intelligent Manufacturing Research Center, IMRC, of National Cheng Kung University, NCKU, proposed the IFA system for intelligent factory automation. The IFA system has been applied to the actual production lines of the partner companies. The vision of Industry 4.1 is to enable the production line to achieve the goal of zero-defect manufacturing without producing defective products. This study utilizes the next-generation virtualization technologies, Docker and Kubernetes, big data analysis, Internet of Things, edge computing, AVM, and IPM to develop a digital manufacturing system that can be applied to the domestic manufacturing industry, which is briefly called DTiM. IMRC also collaborated with Dassault Systèmes, Industrial Technology Research Institute, ITRI, and FATEC to develop the virtual production line applications for machine tools. Now, we are going to demonstrate how to create the digital twin of production line by integrating the virtual and the physical environment as well as to optimize the process quality in real time. First, build a cloud platform. Then deploy it into the private cloud of IMRC, together with the AVM and IPM cloud intelligence services. For the machine tool, the automated production line for aluminum wheels provided by FATEC is adopted. The CPA is used to collect processing information of the machine. The above-mentioned product DT and EQDT information is uploaded to the cloud database. Users can then use this information to create the digital twin metamodels. Utilize virtual 3D platforms, such as Dassault Systèmes 3D Experience to deploy FATEC's automated production lines to a cloud-based platform. And generate a virtual production environment. The EQDT and product DT of the product and machine can be deployed to the edge platform. During actual processing, the AVM, IPM, and other services in the cloud can be accessed via this digital platform. The prediction results and product quality can be acquired in real time to achieve the goal of total inspection. Users can feedback to the actual production line to simultaneously modify the manufacturing processes. When processing improvement is necessary, the NC program is generated and fed back to the machine for further measurement and validation on the physical side. At the same time, the synchronized simulation, verification of loading and unloading, and whole processing can be completed in this digital twins platform. Through the circulation of integrating the virtual and physical production environment, there is no need to wait until the production is completed for the customer's QC department to inspect the product quality. In this way, not only CPK can be improved, and the risk and cost of physical verification can be significantly reduced, but the prediction on the future state of the machine and the remaining useful life of key modules can be conducted. Remote maintenance is also made feasible, so as to save maintenance costs and improve overall equipment efficiency. Automatic Virtual Metrology, AVM. Before starting the production line, first of all, let's introduce the environment of the production line. The lower left corner of the screen shows the actual production line and the location of the machine. The upper right corner shows the EQDT. It can be observed that the simulated locations of machine and robot positions are the same as those on the actual production line. The product DT is displayed in the bottom right corner. Here we can see the prediction values when the wheel processing is finished. There are currently 4 wheels in the product DT display, mirroring the actual situation in the production line. After the machining process is finished, it will show the prediction values. Next, we see the actual process of wheel machining together with its prediction. We will use the wheel model WP892 for demonstration. When the robot starts to work, EQDT will conduct simultaneous simulation according to the movement of the robot. When the production line is running, the internal processing data of each machine in the production line will be uploaded to the cloud database via CPA. When processing is completed, the AVM system will execute real-time prediction and send the result back to the product DT. Next, we can see on the screen that when the robot clamps wheel 66 from the machine EQ1, the wheel ID and its prediction value disappear from product DT1 at the same time. When the robot places wheel 67, the product DT displays the wheel and the ID of the placed wheel again. When the robot moves to machine EQ2 to clamp the wheel 65, the wheel ID, and prediction value are also cleared and disappeared from product DT2, just as in product DT1. Next, after machine EQ2 places wheel 66, the product DT shows the wheel along with the correct wheel ID again. In the same manner, when the wheel 64 of machine EQ3 is clamped up, wheel ID, and prediction value are cleared from product DT3. When machine EQ3 places wheel 65 ready for machining, product DT3 displays the wheel and wheel ID again. The robot turns to machine EQ4 and clamps wheel 63. The wheel ID and prediction value are cleared from product DT4. At this time, the processing of machine EQ1 is finished. Product DT1 will display the prediction value in real time. Next, EQ4 will place wheel 64 for machining. Product DT shows the wheel and its ID. At this point, one wheel has already been processed in the production line. The robot will send the processed wheel out of the production line first, and then go back to clamp a new wheel for processing. When EQ1 machine is ready to process the second wheel, and wheel 67 in machine EQ1 is clamped up, machine EQ2 also finishes machining and the prediction value is shown. While the robot is trying to place the wheel on machine EQ1, EQ3 also finishes machining and the prediction value appears. At this time, the robot has also finished placing the wheel 68 on machine EQ1. The robot moves to machine EQ2 and clamps wheel 66. The wheel ID and prediction value are cleared from product DT2 again. After the robot clamps the wheel of machine EQ2, machine EQ4 finishes machining and the prediction value appears. After machine EQ2 finishes placing wheel 67, the wheel and wheel ID are displayed again on product DT2. The robot goes to machine EQ3 and grabs the wheel 65. The wheel ID and prediction value disappear from product DT3. After machine EQ3 finishes placing wheel 66, the wheel and wheel ID show up in product DT3 again. Next, the robot of machine EQ4 clamps wheel 64. Again, the wheel ID and prediction value disappear from product DT. After this, machine EQ1 completes wheel machining and the prediction value is displayed. And the warning of RI and GSI abnormality is found in the prediction value. This is the AVM prediction result. The abnormal parameter data are sent to the EQDT so that engineers can be the first to know when the system detects a change in machining process that increases the cutting amount per time unit, which leads to an alarm of parameter anomalies. The product DT not only displays the abnormal values, but also sends out alarms on the processing items. Users can conveniently observe the changes of the wheel caused by abnormal processing. Click on the abnormal RI and GSI value. The analysis of prediction value anomalies will pop up. Pareto chart is used to rank the importance of the parameters and to inform users the main cause of the abnormality. The system then immediately sends alarms for the engineers to judge and solve abnormal conditions of the tool or machine. In this case, the system detects a drift of machining path and AVM predicts that this may cause processing quality deviation. Now we can see three interfaces in display. Abnormal processing path values can be examined in the upper right line chart of parameters. The bottom right is a table showing detailed information of the parameters. The left side shows the parameters used for the prediction. Users can click and switch to check different parameter information. Once the wheel processing is completed, this wheel will be put on the CMM measuring machine. Its measurement results will also be uploaded to the cloud database for AVM to update the model to ensure the freshness of the prediction model. The values measured by CMM are fed back into the AVM model for users to verify the accuracy of AVM prediction and find out the causes of machining quality anomalies. As we can see, the metrology values for all the wheels prior to wheel 67 are shown while waiting for wheels 67 and 68 to be updated. The prediction value of wheel 72 in machine EQ1 is also displayed on the product DT. Wheels 71 and 70 are still in processing, so there is no prediction value yet. The current value of machine EQ4 is empty because the robot is at EQ4 and is ready to place wheel 69 for machining. The currently updated metrology values are the values of wheel 67, which are very similar to the AVM prediction values. Next up are the values of wheel 68. Some values are found abnormal due to the deviations of machining path, which are alarmed by the AVM system. This proves that AVM has the capability of real-time warning on processing abnormality. Actual measurement also indicates poor processing quality. Users can clearly observe the current operation of the production line in real time via product DT.